This video concerns Gauss Quadrature. It's a very interesting idea to evaluate integrals numerically. Now, before we go into the typed material, I just want to point out that we have looked at Trapezoidal Rule, Simpson's 1/3 rule, Simpson's 3/8 rule in the videos already. Now, if you look at trapezoid rule, if you look at this segment between x0 and x1, the integral turns out to be h by 2 f0 plus h by 2 f1. What you see is the integral is equal to the f values multiplied by some weights. The weights here happen to be h by 2. The f values correspond to what are given in the data table for us. So the integral is a weighted combination of the f values. In trapezoid rule, the weights are h by 2 for the first data point and h by 2 for the second data point. Now when you come to Simpson's 1/3 rule, the integral is over a range x0 to x2. So x0, x1 and x2 are the three data points that are considered in the basic element, and then we derived this formula, right? Simpson's 1/3 rule gave us this result. So I can expand this into h by 3 f0 plus 4h by 3 f1 plus h by 3 f2. So again, the integral evaluates to a weighted linear combination of the corresponding f values. So f0 and f2 are given a weight of h by 3. f1 has a weight of 4h by 3. So the weight for f1 is 4 times the weight assigned for f0 and f2. Nevertheless, the integral equals a weighted combination of the f values. And the f values, which are f0, f1 and f2 in this case, happens to be taken from the table. That means you do your experiments, collect the data, and you arrange it in that order that you see in the table, and that will determine f0, f1 and f2. Now if you come to Simpson's 3/8 rule, this is what we derive. And I can expand it like what you see here. And again, it is very clear that the Simpson's 3/8 rule, which is based on 4 data points, x0, x1, x2 and x3, the integral of the function between x0 to x3 equals what you see here on the right hand side. This is what we derived. Again, it takes the f values of the concerned data points, multiplies each of them by a certain weight, and then the sum gives us the value of the integral. The sum gives us the value of the integral. So the basic idea that we have to take in mind before we pursue ahead here is that the value of the integral by trapezoid rule or Simpson's rule, the rules that we have looked so far, is equal to a weighted linear combination of the f values. If you place your attention on this part on the top right, I have just said that the integral of the function f of t dt from t is equal to -1 to +1 is equal to w1 ft1 plus w2 ft2 plus w3 ft3. I'm using 3 points here, 3 values of t, which are t1, t2 and t3. So this would be called a 3-point Gauss quadrature, 3PGQ. Now W1, W2 and W3 are the weights. T1, T2 and T3 are the points at which I would need the value of f. Once I have the weights and the values of the function at those 3 points, I can evaluate the value of this integral. So this kind of idea, the value of integral being a weighted linear combination of the f values at specific locations, comes from here, from trapezoid rule, Simpson's rule, etc. The beauty is that the weights are not known. W1, W2, W3 are not specified to be anything. We have to find them out. It is not given to be h by 2 or h by 3 or 4h by 3 or 3h by 8, 9h by 8, etc. It is just left as W1, W2 and W3. Again, the locations at which we have to evaluate the function. That means we have to evaluate the function at T1, at T2 and T3 in order to evaluate the right hand side. The T1, T2, T3 values are not specified to us. We have to find that out. So this works very well, as you will see later, when the form of the function f is known to us. then we can evaluate the function at very different points. For prior data, this Gauss quadrature method is not readily available. You can make it amenable to Gauss quadrature method. I'm not saying this cannot be used, but the Gauss quadrature idea is specifically used when you have complex functions and you want to determine at which points you should sample the function in order to evaluate the integral. So this takes us to something called experimental design. In Trapezoid Rule, in Simpson's rule, etc., the experiments are already done and the data is given to us. Now with Gauss quadrature, you still have to decide what values are to be taken for T1, T2 and T3. Therefore, the experimental points can be determined using the ideas that I'll be discussing later. So basically we are asking what is the best values of T, that is T1, T2 and T3 in this particular case, that I should evaluate the function. And with what weights W1, W2 and W3 should I associate those values of the function. And once I have all of that, then I will be able to find out the value of the integral. Some parts may be clear to you as of now, but some parts hopefully will become clear by the time I end this video. Now, what we are going to say here is, this is the problem we are interested in. Integral a to b, some function f star of x dx. So this is our original problem. Let's say we know this function f star of x that's given to us. That function may be complicated so that analytical integration is not possible. So you have to resort to a numerical way of solving it. And that is what we are trying to find out here. Now, the claim here is this integral of the function f star of x from a to b can be converted to this generic problem. You can make it the integral of a function f of t, which is related to f star of x. But we are getting a new function f of t here. And the integration, of course, will be with respect to t because the variable has changed from x to t. And the limits being from -1 to 1. I'll justify all of these shortly and also show some examples. And then this integral can be multiplied by b minus a by 2 to get the original integration answer. So this integration is going to be exactly the same as this integration. That's how they have set up the problem. So in the answer, there will be no distortion. But the way we do it is interesting and clever. So any problem can be converted to this problem. It doesn't matter what a and b are in our original problem. It doesn't matter what f star of x that function is. You can convert this integral to what you see on the right hand side, b minus a by 2 integral minus 1 to 1 f of t dt. And how do we do that? Simple. We just use this transform connecting the original variable to the new variable. So I'm just going to say x is equal to b minus a by 2 times t plus b minus a by 2. So if this is something you will accept, then dx will be b minus a by 2 dt. Now this is where dx becomes b minus a by 2 dt. And we must convert f star of x into f of t by using this. So in your original function, wherever you see x, you should replace it by b minus a by 2 times t plus b minus a by 2. When you do that, this problem becomes this problem. So the focus going forward will be on this. But before going to that, let me just show you a couple of examples. Now let's say we are trying to integrate the function 1 by x dx from 3.5 to 3.9, right? So this is the problem we are solving. I know you will laugh at this because 1 by x is not a complex function. It's an easy function. You can integrate 1 by x dx and get natural logarithm of x. And then you can easily find out the value of this integral that is given there. So that's not difficult. But let's pretend that 1 by x was a difficult function to integrate. Because once we get into easy problems with such examples, then we can explore some complex problems. Always the teacher does the easier things and we leave the difficult things to students because that is what makes you learn. In any case, so f star of x in this case is 1 by x and then dx. This matches with what we have on the left hand side, right? Some integral a is 3.5, b is 3.9, f star of x is 1 by x and we have dx. So what is the transformation I'm going to use? X is equal to b minus a by 2 times t plus b plus a by 2. This is exactly taken from here. So what you can see is this is a linear transformation, right? This is a linear function. So we are linearly transforming x using what was given in the previous slide. Now you can see when you put t is equal to 1, x becomes 3.9. So in the integral for t, we know 3.9 translates to t is equal to plus 1. X is equal to 3.9 translates into t is equal to plus 1. And you can see the reason here. Put t is equal to 1 and then x becomes 3.9. Or the other way is put x is equal to 3.9 and you will find t is equal to 1. So when you put x is equal to 3.5 in this equation, you will get t is equal to minus 1. So 3.5, the lower limit of the integral for x, becomes minus 1 for the integral with respect to t. So this transformation makes t is equal to 1 when x reaches its upper limit and makes t is equal to minus 1 when x reaches its lower limit. So this integral will become minus 1 to 1. Of course, let's not forget this b minus a by 2, which is going to be 3.9 minus 3.5 by 2. And f star of x was 1 by x. Therefore, how do you get f of t? Wherever you see x, replace it by this expression on the right because x is equal to 0.2t plus 3.7. The f star function is 1 by x, so I'll get ft by replacing x with 0.2t plus 3.7. And therefore, this original problem between the limits 3.5 to 3.9, f star of x dx becomes this. 3.9 minus 3.5 by 2 integral minus 1 to 1 by 0.2t plus 3.7. The integral is with respect to t. So this is how you convert problems from the x domain to the t domain. Now let's take another example. Integral 0 to 1, 4x by 3 plus x squared dx. Let's again pretend this is a hard f star function that we cannot solve analytically. All right, let's pretend this is a hard problem. And the limits are from x is equal to 0 to x is equal to 1. Of course, we know we can solve this problem quite easily by hand. But pretending that it is a difficult function, so I note this. A is equal to 0, b is equal to 1. And once I recognize that, I'll put it in the expression for x for the linear transformation. So x is equal to b minus a by 2 times t plus b plus a by 2. So in this particular case, for the values of a and b relevant to this problem, x becomes half t plus half. So 0.5t plus 0.5. So the original integral now in terms of t, the limits are always going to be from minus 1 to 1. That's what this transformation does. You can see when you put x is equal to 0, t will be minus 1. When you put x is equal to 1, the upper limit, t will be equal to plus 1. So that's what we want on the right hand side. And b minus a by 2, that term is half. Let's not forget that, right? I'm talking about this term. So b minus a by 2 in this case is half. So that half is here. You can pull it out of the integral if you want, like I've done here. So dt. Now in the function f star, wherever I've seen x, I have replaced it by half t plus half. So 4x becomes 4 times half t plus half, which is going to become 2t plus 2. So I can write the numerator as 2 times t plus 1. I can write the denominator as 3 plus x squared. X is nothing but half t plus half the whole squared, because x is this, so x squared. So I'm going to take half t plus half and raise it to the power of 2 in the denominator. So I'm going to get 3 plus t squared by 4. When I expand this, I'm going to get 2 times half t times half, so t by 2, plus 1 by 2 the whole squared, which is going to be 1 by 4. So I've left it at that. I've not grouped the constant terms together. I can bring these two things together, etc. We should do it. We can do it. That's not a big thing. But what I'm trying to say here is this is your f of t. So the original problem has become a new problem. For easy problems, it might be seen, why are we doing this? But for difficult problems, you will see that this gives a pretty good advantage. That means with small number of evaluations of the function, you can get very, very good accuracy. That is why this method is very, very popular. And just the thinking behind the process, right? How people solve problems. What a wonderful idea to just observe the results with Simpson's rule, trapezoid rule, etc. And then say, well, I'm going to write the principle in the form of this equation, and I'm going to say what are the best values of W1, W2, and W3, and T1, T2, and T3. That just looks like a fantastic idea for us to learn about. So in any case, I have shown that given a problem in X, you can convert it to a suitable problem in T. One example, the second example, right? So now I'm going to focus on the integral from -1 to 1 f of t dt. Even without going to three terms on the right, like I wrote here, I'm going to just take a very simple idea. I'm going to just have two terms on the right hand side. So I'm going to say this integral is going to be finally a weighted linear combination of the function evaluated at 2 points. The points are t is equal to t1 and t is equal to t2. And the weights are w1 and w2. So now the question is, I know f of t. I know that I have to integrate f of t from t is equal to -1 to t is equal to +1. This is all I know. I do not know these four things, w1, t1, w2, and t2. So I need four clues or four conditions to find out the four unknowns. So the idea is choose a basis set and ensure they are integrated exactly. So I'm just going to take four possibilities for f of t, and I'm going to integrate the left hand side because they are very easy functions that I'll choose for my basis set, and I will equate it to the right hand side, and I will get four equations that help us to find out W1, W2, T1, and T2. So here I'm going to take the basis set to be these four elementary functions in T. 1, T, T squared, and T cubed. You are welcome to take any basis set as long as it works for you. You can take your basis set to be Chebyshev polynomials or Legendre polynomials or Laguerre polynomials, anything that fancies you. But let's keep it simple here. So I'm going to take the first element of my basis set or first function in my basis set, and I'm going to integrate it because the integral is from -1 to 1, right? So -1 to 1 integral of my first function from my basis set dt. So f of t is 1. So if you evaluate integral dt, it is going to be t. And t from -1 to 1 is going to give you 1 minus -1, which is going to evaluate to 2. So if I integrate the first function of my basis set between the limits t is equal to -1 to 1, the answer is 2. Now, when you come to the right hand side, w1, I do not know what it is. But I know the function evaluated at t1 is going to be 1. Why? Because the function is 1 throughout the domain. So whether you evaluate it at t1, t2 or anything, the function is going to be exactly 1. So f of t1 for this function, the first element of our basis set for that function which is equal to 1, this is 1. And f of t2 is also 1 because that function is flat in the range of t. This f of t, right? We are considering from -1 to 1 for the range of t. So this is t is equal to -1 and t is equal to +1. So for all values of t between t is equal to -1 and +1, f of t is 1. That is what our first basis function is. So whether you sample it at the unknown t1 or the unknown t2, you're going to get the function value to be 1. So the first clue we get right is w1 times 1 is w1, w2 times 1 is w2. Therefore, the first clue that we get is w1 plus w2 is equal to 2. So let's keep this equation in mind. The second equation we get is from taking the second function in our basis set, which is equal to t. So if you integrate t between the limits -1 to 1, you're going to get t squared by 2. And between the limits of -1 to 1, this is going to be 1 squared by 2 minus -1 squared by 2. That's how you evaluate definite integrals. So it's going to be 1 by 2 minus 1 by 2, which is going to be 0. So the left hand side evaluates to 0. That's the meaning of this word integrated exactly. Because we can integrate 1, we can integrate t squared, t cubed exactly. We don't have any issues with that. Okay, because they are very easy functions. And therefore, at t is equal to t1, because f of t is t, f of t1 is going to be t1, because f of t is t. F evaluated at t1 will be t1. F evaluated at t2 will be t2. So the right hand side evaluates to w1 t1 plus w2 t2 when f of t is t. So we get the second equation, w1 t1 plus w2 t2 is equal to 0. Now we still have 4 unknown variables, w1 t1 w2 t2. So we need 4 more clues. That is what the next two things will tell us. So the third element in our basis set is t squared. So when you integrate t squared between the limits -1 to 1, you're going to get t cubed by 3 between -1 and 1. So when you do it, you're going to get 1 cubed by 3, which is 1 by 3, minus -1 to the power of 3 by 3, which is going to be -1 by 3. So 1 by 3 minus -1 by 3 is going to be 2 by 3. Therefore, the left hand side evaluates to 2 by 3. On the right hand side is w1. Then what is if f of t is t squared? That's what we have used here. F of t is t squared. If f of t is t squared, f of t1 will be t1 squared. And f of t2 will be t2 squared. So w1 f of t1 which is t1 squared plus w2 f of t2 which is t2 squared. So we get w1 t1 squared plus w2 t2 squared equals 2 by 3. So the third equation that is going to help us is this. And likewise, if you do it for the last term, f of t is t cubed. Therefore, f of t1 is t1 cubed, f of t2 is t2 cubed. Well, w1 is there, w2 is there. That's the right hand side. The left hand side is going to be t to the power of 4 by 4. Integral of t cube is t to the power of 4 by 4. And between the limits -1 to 1, it is going to be 1 by 4 minus -1 to the power of 4 by 4, which is going to be 1 by 4 minus 1 by 4, that is going to be 0. So we are going to get the last equation as w1 t1 cube plus w2 t2 cube is equal to 0. So we have 4 equations overall. This is one equation. This is equations 2, 3, and 4. Now, you can use any method of your choice. I would use, for example, the Newton method because this and this are nonlinear. In fact, this and this are also nonlinear because the 4 unknowns W1, T1 multiply each other. So you are getting an interaction type or a quadratic type nonlinearity. So this is again quadratic type nonlinearity because W1 T1 and W2 T2, nothing is known. So this equation itself is nonlinear. The first equation is linear because it's just W1 plus W2. This is nonlinear, this is nonlinear. So you can use the Newton method to solve it, or you can use the solve features available in Matlab. So I'm just going to say when you solve these four equations, you're going to get W1 is equal to W2 is equal to 1. So W1 and W2 are 1 each, and T1 is going to be minus 1 by root 3, and T2 is going to be plus 1 by root 3. So the integral from minus 1 to 1 f of t dt for any f of t, this is going to be W1 f of t1 plus W2 f of t2, and we have seen that this is going to be equal to 1 times f at t is equal to minus 1 by square root of 3 plus 1 times f evaluated at t is equal to plus 1 by root 3. So these two values for t are called the quadrature points. These are the best points in order to evaluate this integral, assuming that you are satisfied with the accuracy that is going to be provided by those two terms. If I wanted higher accuracy, I would have gone for an extra term plus W3 f of t3. That would lead to 6 unknowns. Therefore, I have to write 2 more equations. So I have to have 2 more elements in my basis set. Maybe I'll go for t to the power of 4 and t to the power of 5 to add to this basis set. And then I'll set up the appropriate equations and solve for W1, W2, W3, T1, T2, and T3. So that is something that can be done. But given that you have chosen to have only 2 elements on the right hand side, this idea tells us that the weights are equal to 1. And the values of t that you should be probing the function at, or the best experimental points, are t is equal to minus 1 by root 3 and t is equal to plus 1 by root 3. So people have already worked on these things to make life easy for us. But we can verify this. As I just showed, when I have two terms on the right hand side, the quadrature points are minus 1 by root 3 and plus 1 by root 3. And the associated weights are 1 and 1. And this gives us an accuracy of the order of h to the power of 3. Because we have involved 1, t, t squared and t cubed. Now, if I wanted to have 3 terms on the right hand side, that means the integral from minus 1 to 1 f of t dt, I wanted to express it as w1 f of t1 plus w2 f of t2 plus w3 f of t3. So I would need 6 clues to find out w1, t1, w2, t2 and w3, t3. So my basis set would be 1, t, t squared, t cube, t to the power of 4 and t to the power of 5. So the order 5 should not be surprising because you have used in the basis set elements till t to the power of 5. So n is 3 as I said earlier, right? The number of terms we use on the right hand side. When you set up the equations and you solve for it, you get t1 to be minus square root of 0.6, t2 equals 0 and t3 is equal to positive square root of 0.6. So the points are symmetrically located about 0 as you can see, right? So that's one fantastic thing. The corresponding weights are 5 by 9, 8 by 9 and 5 by 9. So W1 is 5 by 9, T1 is minus square root of 0.6. W2 is 8 by 9 and T2 is 0. W3 is 5 by 9 and T3 is square root of 0.6. If you go for 4 terms on the right hand side, you would require 8 equations because for the 4 t's and for the 4 w's. So you would require total of 8 equations, and therefore your basis set should go from 1, t, t squared, t cubed, t to the power of 4, t to the power of 5, t to the power of 6 and t to the power of 7. So the order is 7 when you want 4 terms on the right hand side. That means you're looking for high accuracy. So these are the weights that you will get. If you set up those 8 equations and you solve them, you will get the weights W's to be this W1, W2, W3, W4, and the corresponding t's to be t1, t2, t3, t4. Again, symmetry of the experimental points or the probing points. All right, so this would be called 2-point Gaussian quadrature, this would be called 3-point Gaussian quadrature, and this would be called 4-point Gaussian quadrature. And if you return back to the original problem, which was this, and we recast it as this, so kindly look at the previous slides. If I want only two terms on the right hand side, well, this 0.2 is there, so we'll keep it there, we'll keep it there. And then we know for a 2-point Gauss quadrature, the weights are 1, W1, function evaluated at T1. T1 is minus 1 by square root of 3. And W2, which is also 1, times f evaluated at T2, which is 1 by square root of 3. So uh, this is the 2-point Gauss quadrature, and this is what we need to evaluate. So what I did was I took this function. The function is 1 by 0.2t plus 3.7. This is the function. So I took the function and I evaluated it at minus 1 by root 3 to get f of minus 1 by root 3, the quadrature point. So I get a value of 0.279. And I evaluate the same function, this function at t is equal to 1 by square root of 3. I get 0.2621. Then I say the answer for the integral is 0.2 times 0.279 plus 0.2621, which gives me an answer of 0.1082, which in this case happens to be matching the answer that I will get using a 3-point Gauss quadrature, 3PGQ. That also gives me 0.1082. So here a 2-point Gauss quadrature was good enough. Now, if you wanted to see how you might use Matlab to get the results from 3-point Gauss quadrature, here it is. So basically, I clear the workspace, I declare t to be a symbol, and I say f, the function in terms of t is 1 by 0.2t plus 3.7. I'm a little bit careful with brackets. Maybe I use extra brackets than is needed because I want to increase my probability of getting the answer right. So I'm generally very liberal with putting the brackets in the right place, and I use a lot of brackets. In any case, the value of the integral is going to be 0.2. That's the b minus a by 2 that is outside. So w1 times, substitute the value of minus square root of 0.6 in f. So this basically does w1 ft1, and t1 is 0.6 square root negative in 3-point Gaussian quadrature. Kindly refer to the table earlier. So this should make sense. Then w2 is 8 by 9, and you have to substitute the value of t is equal to 0 in the function. So I just put square root 0. In fact, the square root was not needed. Okay, but square root of 0 luckily happens to be 0. So no problem there, even if you had that. But what I meant was substitute in f. For t, you substitute 0. So here f is only a function of t. So I don't have to say subs f comma t comma 0. That's not needed because this is only a function of t. So when I say substitute in f some value, it means it will substitute for the only variable that's there, for the only symbol that's there. So this evaluates w2 t2 and this evaluates w3 t3, right? So w3 is 5 by 9, t3 is positive square root of 0.6. I get this strange looking expression which is full of numbers, but it's still in symbol form. So what I do is I use the usual idea of evaluating what I see here. So I just say eval integ, which is this variable, and then I get 0.1082. So that is what was reported here. That sums up what I wanted to say about Gauss quadrature. I'll stop here. Thank you for your time today.